All right. All right. So for the next part of the video lecture, we're going to study about Aitken acceleration. Aitken acceleration. This is basically the part 2 of our lecture 17. Alright? The idea is basically that we will accelerate the convergence. Remember the lambda that we calculated using that table? What was the formula? The formula was x star minus xk divided by x star minus xk minus 1, right? This was basically the formula we used to calculate the lambda in every step of the iteration. Just refer back to the earlier lectures, you can find it there. We can also write this in this way. Lambda can be basically x star minus xk plus 1 divided by x star minus xk. This is basically how far I am from the root in my current step divided by how far I was from the root in my previous step, in my previous iteration and in my current iteration. Alright. So we know for, let's say for example, if I take my number of iterations to infinity, if I take my limit of k to infinity, where my k is basically the number of iterations, if I take it to infinity, then for x star minus xk plus 1 modulus divided by x star minus xk, we can say that it will always be equal to lambda. Basically, if I take my number of iterations to infinity, this will always converge at lambda, right? The value of this will basically converge at lambda. So this is true if I take my number of iterations to infinity. Let's say for example, if lambda were fixed. Where was lambda fixed? Lambda was fixed, just refer back to the previous lectures, it was fixed in interval bisection. It was basically fixed at every step, interval bisection. The interval was becoming half at every step of the iteration. So how far I am from the root, if we try to figure that out, it is basically same at every step. How far I am from the root at my current step divided by how far I am from the root at my previous step, which gives us our lambda, which is basically fixed at interval bisection. So the interval is basically becoming half at every step. So we can say the lambda is constant and it's fixed. So we basically don't need to take our number of iterations to infinity to find out the value of lambda. We can simply do this x star minus xk plus 1 modulus divided by x star minus xk, and we'll get equals to lambda. So at every step, my lambda, the value of my lambda is fixed. All right. So if I reform this equation and just make some tweaks, we can just say that x star, if I take off the moduluses, if I take off the modulus operators and just write x star minus xk plus 1 is equals to lambda multiplied with x star and lambda multiplied with minus xk. So lambda x star minus lambda xk. All right. So what we are trying to figure out, basically we want to accelerate the process of convergence, where we want to find out the root at a faster rate. We're basically accelerating the convergence process. All right. Let me see if the video is actually being recorded or not. Sorry. Okay. All right, let's continue. So we want to find out x star. So we basically have to separate the x star on one side. So if we do so, x star, we want to basically separate x star on one side, and we want to form an equation that is equals to that actually we can use to calculate the calculate the root. All right, so if we reform this equation and simplify it down and bring the x star on one side, we can basically say that xk plus 1, this xk plus 1 goes this side, minus lambda xk minus lambda xk. So this lambda x star comes here, we take the x star common, and we basically divide by 1 minus lambda. 1 minus lambda. So just refer back to the previous lectures. You know that in interval bisection, our lambda is fixed. What was the value for lambda? My interval was basically becoming half at every step, so my value for lambda at interval bisection is equals to half, right? So I can basically calculate my root using only 3 operations. We need our x naught, which is basically referred to as xk. We need the next value of x, which is x1, and we refer to it as xk plus 1, and where our lambda is basically half, right? So we plug in these values x0 and x1 will come from our initial guess, and this we'll use the interval bisection and use the middle point to calculate this x1, and then we can plug it into this formula and we can calculate the root at an accelerated rate. All right, so if my lambda is fixed at every point or step, all we need is xk plus 1 and the xk. It's pretty simple. Just work out some examples and you can see it. I'll try to include some examples in my lecture notes, so you can see, you can use that to see if you can use that as a reference for how to calculate the root within using xk plus 1 and the value of lambda, which is basically half for interval bisection. All right. So for interval bisection, what is the first thing that I can do? For interval bisection, I can guess my xk and xk plus 1, which is basically x0 and x1, and find the x star within we're using 3 components, x0, x1, and lambda, where lambda is basically half. This is only true for bisection, where lambda is fixed. The value of lambda is fixed, but this is not true for fixed point iteration. Let's see how we can manage our use of fixed point iteration using Aitken Acceleration. Now, moving on to Aitken Acceleration for fixed point iteration. So the problem that we will face in fixed point iteration is that our value of lambda is not fixed. Go back to the example for fixed point iteration, and you can see for the math that we did for order of convergence, you can see the value of lambda is not the same at every single step. So if it's not fixed, we can't directly say that x star minus xk plus 1 divided by x star minus xk is equals to lambda, because my value of lambda is not fixed. All right. So if my value of lambda is not fixed, we can say that, let's assume that x star minus xk plus 2 divided by x star minus xk plus 1 is equal to some lambda. It's equal to some lambda, not the exact value of lambda, just some lambda. All right. And we assume that x star minus xk plus 1 divided by x star minus xk is equals to lambda prime. So we're for the second step and the first for the third step and the second step, we're assuming that the division between them from is basically lambda. We're denoting it as lambda for that step, and for the first and the second step, we're denoting it as lambda prime. So if it is a linear convergence, we will be they will be very close. If it's a linear convergence, the value of lambda and lambda prime will be very close. So let's assume that my value of lambda is almost equals to, let's assume that my value of lambda is equals to lambda prime. All right, we're assuming because they are not the same. They are not the same. You can check the example for fixed point iteration. The value of lambda is not the same at every single step. It converges at one point, so we call it linear convergence. Or if it converges at 0, we call it superlinear convergence. But for fixed point iteration, the value of lambda at every single step is not constant. So please bear that in mind. All right, moving on. So if we assume that my value of lambda and lambda prime is almost equal, so we assume that it is basically equal, lambda is equals to lambda prime, because in linear convergence we can see that the values of the lambda and lambda prime at every single step is almost very close. The difference is very minimal. So we are assuming that lambda is equals to lambda prime. So using this assumption, we can basically write x star minus xk plus 2 divided by x star minus xk plus 1 is equals to x star minus xk plus 1 divided by x star minus xk, using this assumption. All right, so moving on to the next step, we have to derive a value for x star. The next step is we have to derive a value for x star. All we need to do is basically cross multiply and just bring out x star to one side. All right, so we cross multiply and we end up with is basically x star square minus x star xk minus, I urge you to do it alongside with me. Just do the math yourselves alongside the video so that you can keep in pace with me. All right, x star minus x star multiplied with xk plus 2 plus xk multiplied with xk plus 2 equals to x star whole square minus 2 x star into xk plus 1 plus xk plus 1 whole square. All right, so if we simplify it and bring the x star, basically the root terms to one side, basically the x star to one side, just a simple simplification. You can cross out this x star because both are on either side of the equal sign. This is a simple algebraic manipulation. You can find simplify it down to x star is equal to xk minus, I'm not going in depth with the algebraic simplification because you are very much capable of doing that yourself. So xk minus xk plus 1 minus xk whole square divided by xk plus 2 minus 2xk plus 1 plus xk. All right, this is the formula that we have derived for x star. Bear in mind that we are using xk plus 1 and xk plus 2, and we are you might think that we are gonna go to the root directly. Not exactly. We're gonna make jumps because we're assuming that lambda is equal to lambda prime, which is not. We are making an assumption here. So we can make a great jump, but we don't actually reach the root. So for convergence, which are very slow, we'll see an example right now. For convergences, for fixed point iteration, which are very slow, we can basically use this Aitken acceleration to make bigger jumps, so that we can make bigger jumps and reach like 30 or 40 or 100 steps ahead. All right. So basically, to do this, we need three things and three steps we can find. Xk, we'll need xk, we'll need xk plus 1, we'll need xk plus 2, and we're not exactly calculating the x star using these three variables. Using these three variables, we're not exactly calculating x star. In turn, we are calculating xk plus 2 hat. Basically, we are jumping on to an closer root assumption rather than going to the root itself. All right. So that we denote by xk plus 2 hat. You're gonna see it in the in a few minutes how we are gonna calculate it. All right. So it for xk plus 1, xk plus 2, you can basically easily calculate it using a g of x, which you will be given in your question paper. It's basically fixed point iteration, so the g of x will be given to you. So you can easily assume x0, x1, and x2. And using these three variables, you can assume calculate x2 hat. All right, you can basically calculate x2 hat using these three variables, and I'm going to show you how to do it. All right. Hence, my x star is, we have to see that my x star is not perfect. So if my lambda and lambda prime are closer, they are more accurate. The more closer that my lambda and lambda prime are, the more accurate my answer will be. So basically, we can make huge jumps across the iterations. Let's say, for example, fixed point iteration that takes about 600, 500, or 700 steps. So we can basically make dumb it down to 8 steps or 9 steps using Aitken acceleration. All right, we'll just we'll see how we can do that. So xk we can easily calculate using fixed point iteration. Xk plus 1, same. Xk plus 2, same. So using these three variables, we have to calculate xk plus 2 hat, which is basically the same formula that we designed for the root, which is xk minus xk plus 1 minus xk square and xk plus 2 minus 2 into xk plus 1 plus xk. We used this formula for the root in the previous previous step where I derived the formula, but I said that doesn't give me the exact root. We're basically assuming that lambda is equal to lambda prime, and we are making a big jump. All right. So this is how we calculate xk plus 2 hat. All right. So we basically need this to accelerate the fixed point iteration process. It is not the same as xk plus 2. It's we calculate it using this formula. All right. Let's jump on to an example. All right. I'm gonna set it. All right. Let me set it like this. All right. Jumping on to an example. Let's say I have a function f of x is equals to 1 over x minus 0.5. All right. This is the same example that you will find in my lecture notes, so you can use that side by side so that it is easier to understand the notes. All right. So let's say I have a function 1 over x minus 0.5. The root, I can easily say the root of the equation, which is x star, is equals to 2. Basically, you plug in f of x equals to 0 and find out the value of x, which find out the value of x, which is actually my root. So what do we need next? We need a g of x, a map g of x, which is let's say x plus 1 over 16 into f of x. How did we come up with this formula? Just simply plug in this into f of x and plug in x into g of x and just backtrack and see if you can find out this formula using this. Alright, we basically plug in f of x equals to 0 and then reform the equation with x on one side so that we can form a g of x. But in this case, we're basically doing the reverse of what we were supposed to do. But you actually don't need to understand this process. Just bear in mind that g of x, you need to have bear in mind that how to calculate this f of x. We basically, for any given g of x where the x will be set, just calculate the function, the value of the function at that x basically, and multiply it with 1 over 16 and add it with the x itself. So let's say my initial guess, which is x naught, is equals to 1.5. Alright, before I move on to the math, I just want to see how my convergence is. So we basically use g prime of x to find out the value of lambda, which actually shows us how the convergence of the whole process will be, whole iteration will be. So basically g prime of x is equals to 1, because basically the first derivative of this g of x. X will give us 1 plus 1 over 16 into f prime of x. So basically plug in the x star and g of x will give you the lambda. So g prime of x star is basically equals to lambda, which is equals to 1 plus 1 over 16 into the value of the first derivative of the function. Let's calculate the first derivative of the function. First derivative of the function f of x, f prime of x, is equals to minus 1 over x squared. We just did differentiation on this function. Alright. So g prime of x, if we plug in the value of the root, which is equals to 2, into this, is basically into f prime of x gives us minus 1 over 4. Alright. So we can use this formula to calculate the value of lambda, which eventually comes into 0.984375. You can see that the value of lambda is less than 1. So basically my map will converge. It's basically a contraction map. My map will converge at a root, but it will do so very slowly. It will do so very, very slowly because the value is less than. Basically, just think about interval bisection. The value of lambda was what? Half, right? So at interval bisection, the value of lambda was half. So here it's basically almost twice much than what it was in interval bisection. So in interval bisection, we usually take about 80 to 90 to 100 to even 200 steps. So here we might even need more than what my interval bisection would have given me. All right. So for this specific example, let's say for example, let me show you how many steps it would take if I used fixed point iteration on this specific, or using this specific mapping g of x. All right. If we started with our x naught equals to 1.5, all right, for x1 we'll get g of x naught. All right. For x2 we'll get g of x2. From g of x2 we'll get our x2. If we continue this process, g of x1, g of x1. All right. If we continue this process, at the 818th iteration of this whole map fixed point iteration, if we continue it, and at the 818th iteration, we get the value of our root to correct to 7 decimal places, which is basically 1.999999. At the 818th step, we're getting an x star correct to 8 decimal places. So it is taking us very long to figure this out. Basically, we get it to correct to 8 decimal places. It's taking very long to figure out the root using fixed point iteration. So now we'll use Aitken acceleration on this map so that we can accelerate the whole process and reach the root in basically 8 steps. Let's go move on to the map. All right. So basically for Aitken acceleration, what did we need? xk plus 1, xk plus 1, xk plus 2, and using this 3 variables we used it to calculate xk plus 2 hat. So let's say our xk is basically x0, this is x1, this is x2, and this is x2 hat. All right. So x0 is basically 1.5, our initial guess, which was, and if I plug in x0 into the map g of x, we get x1 equals to, if we plug in x0 into g of x, so g of x0 is basically x1, which will eventually give us 1.510417. Very small jump. Just think about the difference between the step and the previous step, the value. It's very minimal. So that is how it takes us 818 steps to actually get a value correct to 8 decimal places. All right. Okay. Moving on. So if we plug in g of the value of x1 into the g map, we'll get x2. This comes out as 1.520546. Once again, I'm not showing you how to calculate these values because you already know how to calculate it. Just use this value and plug it in to this formula. The f of x, use the same value of x0 and plug it in so that you can get the value of the function, multiply it with 1 over x, and then add it with the value of x, which is 1.5. Then you'll get x1. Same thing, you repeat the process, plug in x1 and you'll get x2. Same. So for this one, x2 hat, what did we need? We needed xk minus xk plus 1 minus xk square divided by xk plus 2 minus 2 into xk plus 1 and plus xk, which is basically nothing but x0 minus x1 minus x0 square divided by x2 minus 2 into x1 plus x0. So just using these 3 values, you can calculate this. This comes out as 1.877642. Just see the massive jump that I have made to calculate my root. The massive jump. See, at every single step, the minimal change. The change was basically almost very minimal. But at this step, I'm getting very close to the root with a single calculation. Which was, we assumed that our lambda is equals to lambda prime. We made this assumption to make this jump. So we're basically accelerating the process. So the next part, this was part 1 of the whole math. For the next part, you'll assume that x3, which is my third value of x, is equals to x2 of hat. I'm just assuming that x3 is equals to x2 hat. Basically, process take continue kortesi arki. x3 is equals to x2 hat and x4 is equals to g of x3. Just x3 plug in korbo g te, we'll get x4. x5 er jonno g of x4 ta plug in korbo, so we'll get x5. So eta we know from this step j, it is equals to 1.877642. This will come out as 1.88164223, and this will come out as 1.883608. Once again, use this value, the value of x3, plug it into the map of g, and you'll get x4. Just simple math. Do it yourself. Try it. Otherwise, we'll go into discussion. Use where in the weekend I'll try to do a discussion in Google Hangouts. I'll review your problems if possible. All right. So what is the next thing we do? Calculate x5 hat, which is equals to, same thing, we'll treat this as xk, this is xk plus 1, and this as xk plus 2. So x3 minus x4 minus x3 square divided by x5 minus 2 into x4 plus x3. All right. This gives us 1.9930691. See, I'm making another great jump. Basically, our root was what? Our root x star was equals to 2. See how close I got within x5? This was part 2. If I continue this process and calculate x6, which I'll assume that it is equals to x5 hat, and calculate x7 using g of x6 and x8 using g of x7, and when I calculate my x8 hat, it will give me exactly 2. You just continue this whole process. Once again, this is basically part 3. You have to do it yourself and just see, and you'll get the root, the value of the root 2 at x8 hat. All right. So see, we're using basically how many steps? 1, 2, 3. X naught is basically given, so we're using 1 step, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right. If you disregard these steps, where x3 I'm assuming is equals to x2 hat, where basically no calculation is needed. 1, 2, 3, 4, 5, 6, 7, 8, 9. Basically in 9 steps we are calculating the exact root of the function. Whereas in my fixed point iteration, if we use the normal formula rather than opting for Aitken acceleration, we would have taken 818 steps to get the answer only correct to, I guess I made a mistake. It was only correct to 7 decimal places. I get an answer correct to only 7 decimal places. All right. So this is basically Aitken acceleration, which was part 2 of your lecture. I'll upload an assignment I'll upload it, the assignment number 4 in my Google Classroom. The deadline will be next Wednesday. So please use this video as a reference to solve the maths. All right. Thank you.